Hello everyone, this is the video demonstration for EE542 Lab 4 where we design our own custom fast reliable file transfer protocol. So let's start. So a basic rationale is we want to create a protocol for a network with like high bandwidth but also high delays and also in certain situations high losses. So generally the TCP performs pretty bad in this particular situation in these situations. So we try to design our own custom protocol so we can increase the performance to the max if possible. So this is the current protocol I've designed. So let's see how it works. So as we know, TCP, we send data wherever window and we receive ACKs accordingly, and then we increase the window and go go that way. So in this particular protocol, so in the initial round, we send all the entire data. So we send the entire file to the receiver. So for example, let's say it's going to be a 1 GB file. In our case, it's a 1 GB file. We're going to send all the entire data through packets to uh, the client in the first round. So each packet is going to be of 9,000 bytes because we have set the MTU as like 9001, and we don't want to go to the IP layer to further fragment the datagram and waste more time. So we have set the MTU as 9. So we have set the buffer, the size of the packet as 9,000. So in the first round, all of this is going to go to the receiver. So what happens is we're going to try our best to send at a maximum rate possible. So it's possible that losses will be induced in this round one situation also. So yeah, so it's possible that losses can be induced because a buffer overflow in the router. So what happens is, so after this happens, so the client knows that it has missed some data. So then the client is going to request those packets it has missed, or those particular packets that have been lost to the client separately, to the server separately. So the so sorry. So now the client is going to send me packet one, and the sender is going to send packet one. And for example, the client is going to tell the sender send packet 126, and the sender is going to send packet 126. When all of this is done, our whole file transfer will be complete uh, and done. So we've seen that in the round two, where the client is gonna tell the sender to send data. But let's see how the client knows this stuff. Like how does the client know it has missed packet 126? How does the client know it has missed packet one? So let's see in the next slide. Okay. So what happens is first let's before that let's just take a clear look at our packet and how we've designed it. So then we can understand how it's done. So we have a data, and we also attach the packet ID and packet size to the header. So let us look at the packet size. So the packet size is generally 9,000 bytes. But for example, it's possible that the last packet will have less than 9,000 bytes if the file size is not equally divisible by 9,000. So it's also pretty important to include the packet size. So in the client side, the client knows how to index the local array to copy this file. So it's pretty important. So we have seen that when we send the packet, we also send the packet ID. So in this way, the client will know the identity of the packet that's coming. And before all that, before all this happens, we can see that in the first transmission from the sender to the client, the sender sends the file size and the number of packets to the client. So this is really vital. So even before the transmission of the data starts, the sender is gonna send basically the number of packets and also the file size. So when this happens, the client knows that it has to receive these many packets. And also, since we have identified each packet in the header, so the client knows what packets it's receiving. And also we create an array. So let's look at that in the next slide. So this is what we have done. So we've initialized an array of size packet count. That's the total number of packets. So this is so let's, for example, if the file has 5,000 packets, this is gonna have 5,000 this array is going to be of size 5000. So initially we're going to set the values as all the values as 0. And what we're going to do is, when a packet comes, for example, let's say this a packet 25 is coming. So, and this packet 25 is going to be the number is going to be addressed over here, and the data is going to be over here. So when this packet is received by the client, the client knows that, okay, so this is the packet ID 25. So I'm going to put a 1 in index number 25. Similarly, let's say packet 50 comes, the client is going to look at that and say, okay, I've received packet 50. Let me put a 1 over that to show that I've received it. So all this happens, but for due to some reason, packet 100 is missing. So we've seen that since we have initiated as 0, this is still going to remain 0 even after the first round of transmissions, because we haven't received packet 100. So this is the way we're going to identify the packets that need retransmission. So we can see that initially, so yeah, so we can see it's gonna send a okay, it's supposed to be 100. It's gonna send a packet 10 or packet 100 if it's lost or not received, and then the sender will send this particular packet. So we can see that this index will send the send a request to the sender to send the corresponding packet. Okay, so now that we have seen the basic idea of a protocol, we have to look at improving the performance. So the main thing about improving performance is making sure we access all the data in the memory rather than going to the hard disk all the time. So consider a situation where we're like putting data into the packets. We don't want to read from the file every single time. So if this happens, we're going to incur page faults, and this is like years and years of time in computer in the scale for the in computer time. So what we do is we take the entire 1 GB file and we put it into a RAM using dynamic allocation. So in C is going to be malloc, and C++ we use new. And also on the client side, every time we receive a particular packet, we don't write into a file, we put it into a local buffer, and after we've received the entire data, we write it into the file. So I also observed that doing this increases the performance literally 2 times. So it's really important to put the data into the dynamic memory, put it into the memory rather than having it in the hard disk. That can cause huge delays, uh, and the process will actually stop for like 10 milliseconds until it receives the data from the HDD. So it's pretty important. One thing to note that some OSs have clever cache mapping methods to make sure to reduce page faults, but still it's imperative to make sure we don't read anything from the HDD while running the program. Okay, so now let's look at the program flow. We simply explained it in the previous slide. So let's take a look, like a diagram. Let's take a look. So from server side, we're gonna get the file name from the client. So then what we're gonna do is we're gonna read the file, and so basically we're gonna read the file and put it into a local buffer in the memory. So then we're going to send the file size and the number of packets to the client. So this is important, very important, because this is the way the client knows what packets it has to receive and what packets it hasn't. So so now, so what happens is after this, okay. So the client knows how much data is to receive. Now the server will start sending the data. That is pushing out data using send to without any. It's going to like push the data out. It doesn't care. It doesn't right now. It doesn't care if the client is going to receive fully or not. It's going to push data out as fast as possible. So what happens is, after completely sending all the packets, the server goes into the retransmission mode. So what happens is, now, so we're going to see from the client side also, the client is going to look for the last packets and is going to request the lost packets. So our job as the server is to transmit these lost packets to the client, and at one point the client will send a flag to say that I've received all the packets, let's stop, and we have completed file transfer. So this is the client side. So we're going to get the file name from the user, where we're going to type it in the command window. Then we're going to send this file name to the server, where the server is going to read the entire file and keep it ready. And also, we can see we're going to receive the file size and the number of packets from the server. So what we do is, then we saw that the server is going to push out data as fast as it can. Now also we use receive from to receive the packets. So generally during case of packet loss, we won't get all the packets in here itself. So that's why we gotta ask the server again. So simultaneously, as we've seen, we're gonna fill the array with ones if we receive that particular packet, or else it's gonna stay as 0. So what happens is, if even one element in the array is a 0, that means we have that means at least one packet has not been received. That means the file, the transfer hasn't been completed yet. So what happens is, in this particular case, we're going to use these indexes to ask the server to send those particular packets. And when it has been completed thoroughly, we're gonna complete the file transfer. So let's look at the program code to further understand it more. So let us look at the server-side code right now. So we create our structure. Uh, so remember the slide where we showed our how our packet looks. So that's how we defined it in a structure right here. So then we just simply create a bind a socket to a port, and we wait for the client to connect. And here we're going to receive the file name from the client. So after this, what we're going to do is we're going to open the file, and then we're going to find the file size. So for that, we seek to the end of the file, and that's the file size. And then we rewind to basically basically read from the file. So right here we can see we're going to read from the file, and this info is the local buffer I was talking about, with the size of file size plus 1 to include the last character of the file. So this is the step where we talk about what happens if the last packet it doesn't have 9,000 bytes and have less. So if file size is equally divisible by 9,000, that's the size of the packet, then then the packet count is going to be file size divided by buffer size, straightforward. But if it's not equal, that means the last packet is going to have less than 9,000 bytes. So this command. So we have to we have to identify what's happening. So we set a flag called the even flag. So we also have to find the length of the size of the last packet we're talking about. So we find the size of the last packet, and we're gonna send the packet count and file size to the client as we mentioned before. So here what happens is, uh, so so here what happens is, yeah. So we're gonna send so we're gonna set I is equal to 1. That's going from packet 1 until the last packet. So that's what's happening here. So we're gonna send every single packet in the first round. So this is the way we're gonna copy from the local buffer into the packet and send it. So even flag means all the packets have equal uh, equal size of 9,000 bytes. So if that's the case, we're gonna copy like this. But if it's not the case, remember for the last packet, it's gonna have less than 9,000 bytes. So we have to index it like differently. So after this is done, we're gonna send the packet to the client. So we can see the packet contains the packet.data. That's going to be this particular section, and the packet length is going to be the buffer size 9,000, or it's going to be the last packet size in this particular case. And also the packet number is also mentioned right here. So the three parameters are sent to the client. So then what happens is this initial round is done. So we can see if packet count is equal to I, that means if the last packet is sent, it means the first transmission is complete, and then we go on to the next phase. So here we can see for the retransmissions, we can see right now we receive the packet ID we have to send from the client, and we can see here we're gonna send this particular packet back to the client. So we also have remember we talked about a control signal where we said if we get a control signal we're gonna stop. So we have set the 0 as the control signal. That means if the client sends a 0, that means the transfer is complete and we're gonna exit. So we can see this is how we do it in the server side. So let's go to the client side. So very similar, the same structure of the packet, and we initialize the socket section of our program right here. And yeah, here we ask the user for the file name, and here we're gonna send the file name to the server. And right here we can see we are receiving. Remember we talked about how we received the packet, number of packets and also the file size. So we receive that from the client here, sorry, the server here, and we do the same calculations as the server to find the to check if the last packet is going to be of less than 9,000 bytes, and also if that's the case, what's the size of the last packet. So same as in the server side. And we also, remember we talked about we create a local buffer to write into. So that's this buffer that we have filled using the file size we received as information. So we start the clock to initiate the file transfer. So we can see right, yeah. So this is the section we're talking about of the array. So we have initialized this array with packet count +1. That's because we don't want to index 0. Basically, we negate 0. So that's why we've done it. And I already set the 0 index as 1. So it's not confusing. Simple as that. So we can see we initialize all the values as 0 right here. And then we go into the loop where we receive all, where we start receiving from the server. So in this case, it's possible if packet loss occurs, we won't get every single data in this particular case. And we can see whenever we receive this packet, we write into that location for the array as 1. And then we can see this is just to show the user what's happening inside during runtime. So we can see we're writing 1. So imagine what happens if packet 2 doesn't come. That means 2 will never become 1, and the index 2 will always become 0. And then we're going to catch that in the end to ask for retransmissions. So again, same with server side. The same as in the server side when if the packet sizes are not equal. So here we're gonna copy the data from the packet into the local buffer, where we're going to write into the file later on after some time. So after this we're going to break, and now we come into the retransmission phase. So again we can see we pass to the array again, and if it's equal to 0 means we've incurred a loss, and we set a flag, and we move accordingly. So again we pass to the file, and if a particular index is equal to 0, remember we talked about how we're going to ask the server to send again. So that's what we're doing. So if a particular index is 0, we're going to ask the server to send that particular packet indexed by C. That's going to be packet ID, and we're going to receive from the server. So remember that packet loss can also occur in these situations. So for example, consider it's possible that this particular at this particular section the packet has been lost. So what we do is we set a timer, and after the timer expires we check if C is equal to the correct packet ID. If that's the case, it means we can go forward and send it to the client, send it to the server. But but what happens is if that's not the case, we again do it to make sure we get the correct packet from the server. So that's what this section does. It makes sure we get the correct packet from the server, battling through the losses that's happening in the system. So after this command, that make sure we get the correct packet for that particular value we indexed from the server. We also send. So what happens is we copy it into the local memory as seen here. The data we received. So here is this iterator to find the last value we're going to send, and this value satisfies. That means we're going to send the last. This is going to the last value. So remember we talked about a control signal. So we send the control signal 0 to the server to say it has been completed. And this is the else case. If all the values in the array were 1, that means we don't need to do any retransmissions because we already received all the data in the round 1 transmission. So this particular case, we skip the retransmission and we complete it, and we finish and we write in the end. So that's the server and the client code. Now let's go to AWS to test the protocol and the systems. We have these three instances where uh, in two subnets and the router connecting the server and the client. So let's go to the command window where we have SSH'd into the three instances. Yeah. So we can start. So in the first case, let's have no loss where we have 200 milliseconds delay and 100 megabits per second in the server and the client, and 80 Mbps in the router. So this case already been set, and okay, there we have it, and let's set the same in the client. Okay, and we already have set 80 megabits per second in the both of the router interfaces. So let's just run a small program now to see, because we don't, or the video will be too long. So let's create a small file right now. Yeah, so let's create a file of, let's say, 1 MB, and let's start. Let's use port 8000. And it's going to be data.text. So it's running. So this is the initial transfer. So what happens is, because there's no packet loss, we made sure we sent all the data in the first try, and we can see we didn't need any retransmissions, or all the data has been sent in the first try. So let's verify it. So uh, we can see we got the exact same file transferred to the client. So we can try the same thing for, let's say, the first case where we had a 10 milliseconds delay and 1% packet loss. So let's try the same thing. Okay, let's try the same code. So we should have retransmissions in this particular section. Yeah, so we can see we had retransmissions. So what happened was packet 84 and packet 88 were lost, and we can see the data wasn't transmitted correctly. That's what the client tells us. Now again, the client is going to ask it to send 84 and 88, and the server is going to send the packet 84 and packet 88. And we can see this is the first section. That's the round one. And for the retransmissions, it sent the respective packets that client asked for. So let's again also let's verify. Yeah, there we go. Similarly, it's done for the 1 GB file. Now let's look at our PPT for further analysis. Okay, so this is the algorithm that's been simplified from the flowchart we created here. So it's pretty much the same thing. So these are the outputs. And yeah, so first let's look at the SAP performance. So this is the protocol we're gonna compare with and hope to increase our performance, and we did. So we can see SCP performs pretty bad in all these conditions. So let's look at the situation for 1% packet loss. It takes a huge hit because TCP doesn't know whether congestion occurs or packet loss occurs. So it considers the packet loss due to the network condition, due to the lossy network as congestion, and throttles the sending rate by, let's say, half, or sometimes even to one, depending on the case, whether it can be timer and also the type of TCP protocol. So while this is pretty bad, we can still manage with this particular speed. However, let us look at the second and third cases. Look, we can see the throughput has been really bad. So this let's look at the third case. So the reason for this is because of the RTT. Because of the huge RTT, it means like after 200 milliseconds only we can seek to improve the sending rate. So, and this takes a lot of time, and we are wasting bandwidth in this particular time where we wait to increase uh, the sending rate. So we can see the throughput takes a huge hit because of this characteristic of TCP that always depends on the RTT. But the situation where the packet loss is included, the throughput takes another huge hit because again, rather than the sending rate being increased in a slower rate, the sending rate is also being reduced repeatedly due to the packet loss. So SCP performance is pretty bad because TCP performs doesn't perform well in situations of have high bandwidth delay product and also packet loss. So this is the analysis of why it happens. We can see that for example, let us consider the AMD situation. We increase, we deal to the loss, we again decrease. We increase, we deal with the loss, again decrease. So our average throughput is going to be really low, and we won't be utilizing the entire bandwidth available. So that's the problem with TCP, where it uh, throttles the sending rate and also its dependency on RTT. So let us look at the performance of our protocol. So we can see for a 100 Mbps link and 200 milliseconds delay, we're getting a throughput of 32.63 megabits per second. So this is around 150 times the throughput of SCP. So our way of sending all the data in the first round and sending only the required retransmissions in the retransmission round provides a pretty good throughput for this particular situation. And we can see the problem with TCP is it has to wait for the 200 milliseconds to gradually increase the sending rate, and also during increasing the command window, it will also hit the ceiling, and again the sending window will reduce, and again it will take a large amount of time for the sending rate to improve. So that TCP performance is pretty bad and our protocol performs pretty good over here. And let's look at the next situation where we have a 100 Mbps link, 1% packet loss, and 10 milliseconds delay. In this particular situation, because of the packet loss, we are like sending gradual, surely more, we're doing surely more retransmissions, and because of that, because of the packet loss, our throughput reduces, but still our performance is 7.5 times the throughput of SCP in this particular case. And we can see generally when empty size decreases, the throughput will also decrease because when it doesn't affect that much without packet loss, but if during packet loss, because more packets are lost for a smaller a smaller MTU size, and we're going to retransmit more number of packets. So that's why the throughput decreases with increase in MTU decrease in MTU size for events with packet losses. So let's look at the next situation. That's the most drastic situation where we have a high bandwidth delay product and also 20% packet loss. So in this situation, our protocol performs with 1.5 Mbps, and but still because during this case we perform much more retransmissions, so that's why our throughput reduces. But still, we can see even in this case our throughput is like 17 times the throughput of SCP over here. When you look at the situation over here, we can see it takes several hours for the 1 GB file transfer to occur, but in our particular case, it can occur over several minutes. So our way of doing initial round of a round one, a protocol of our way of designing a protocol with 2 rounds of transfer, where we send all the data in the first round and then we send the required retransmission in the second round, performs much better than TCP in these conditions. So thank you.